All right, folks, here's our second example of a related rates word problem. I call this one the car chase problem or the car crash problem. Typically what happens is you have two cars, maybe a police car and the robbers, they rob the bank, and the robbers have already turned the corner and they're driving away from the police car. And the police car is driving toward the intersection. They're following the robbers and trying to catch up. Or, that's the car chase, or the car crash. You have both cars. One car is driving toward an intersection, and the other car is also driving toward the intersection, and they're both sort of approaching the intersection at the same time, and they could potentially crash into each other when they get to the intersection. Okay, there's that. Now, there's another variation where it's possible where both cars are driving away from the intersection, and so those two cars are completely unrelated to each other. But it's a little more exciting when you either do the car chase or the car crash, because you kind of want the two cars to be related to each other in some way. Okay, so let's read the problem. It says two cars, car A and car B, two cars are driving toward the same intersection. There's the intersection right there, intersection of two roads, on perpendicular roads. So this road is perpendicular to this road, which means it creates a right triangle. Very convenient, right? Car A is driving south at 25 meters per second, and car B is driving west at 22 meters per second. At the moment that car A is 60 meters north of the intersection, so the distance from the car to the intersection is 60 meters, car B is 80 meters east of the intersection. So now this is 80 meters at that moment. At what rate is the distance between the cars, the straight line distance, which is a hypotenuse, that straight line distance between the cars, at what rate is that distance closing? We're calling it S. At what rate is that distance getting shorter at that very moment? And so notice that the two cars and the intersection, they create a right triangle where the hypotenuse is the distance between the cars. And the two legs are the distances of the cars from the intersection. Okay? So this is another right triangle related rates problem. So the one I call, the car chase problem, in this situation, unlike the ladder problem, in the ladder problem, both legs were changing, but the hypotenuse was not changing. It was constant. In this case, both legs and the hypotenuse are changing. All three sides of the right triangle are changing. So when you're facing a related rates problem where it's a right triangle and all three sides of the right triangle are changing over time, I call that the car chase problem or the car crash problem. That's what I call it. It's a classic problem in calculus, okay? And you'll see it in different variations. I had a few years ago on the AP Calculus exam, there was a lighthouse here, and there was a boat here, and there was a boat here, and this boat, or a ship. This ship was getting closer to the lighthouse, and this ship was moving away from the lighthouse. It was a classic car chase problem, okay? All right, so let's go through our steps here. Step one, identify the given rates. In this case, we're given two rates. We're told that car A is driving south at 25 meters per second, and car B is driving west at 22 meters per second. Since car A is driving south toward the intersection, that's a negative rate of change because the distance is getting smaller. Car B is also driving toward the intersection, so that distance is also getting smaller, so car B also has a negative rate of change relative to the intersection. So we're going to say that dA dt, we'll call this side A, and we'll call this side B, and the hypotenuse is S. You could call it C if you want to, but it's being called S. By the way, it's also very common in AP Calculus for them to call the horizontal line X, like the X-axis, and to call the vertical line y like the y-axis. So why don't we go ahead and do that. We'll call them x and y. So in this case, A is getting closer, so that means the distance y is getting shorter. That's dy dt is negative 25. And so now x is getting shorter. Dx dt, the rate of change, is negative 22 because car B is driving west at 22 meters per second. So we have our two given rates of change. Now, step 2 says to identify the unknown rate. Well, the unknown rate is, it says, at what rate is the distance between the cars s? At what rate is s closing? So that's ds dt. That's what we're trying to solve in this problem. Step 3, is there a formula that relates y, x, and s? Well, it's a right triangle, and those are all distances, so it's a Pythagorean theorem problem. So we'll have x squared plus y squared is equal to s squared. Step 4, plug in for constants. Well, all three of these variables are changing, and therefore we're not going to plug in for anything because all three of the variables in the formula are changing. So we're going to skip step 4. Now let's go to step 5. Step 5 says to do the derivative of each term. Well, the derivative of x squared is 2x dx dt plus 2y dy dt equals the derivative of s squared would be 2s ds dt. And now I want you to notice how many variables we have. We have x, the rate of change in x, that's 2. Y, the rate of change in y, that's 2 more. And then s, and the rate of change in s, that's 2 more. That's a total of 6 variables. So we have to plug in for 5 of them. We're solving for ds dt, so we have to plug in for the other 5 variables. Now, 4 of them are given to us. Look, they gave us dy dt and dx dt, which we wrote down up here. They also gave us car A is 60 meters north. So that means that's y. They gave us y. And car B is 80 meters east. So that is x. So we're going to plug all those numbers into our formula here for step 6. So we're going to have 2. And again, you can divide by 2 all the way through and cancel the 2's. But sometimes my students get confused when I do that, so I'm going to leave the 2's in. So I got a 2. Then x, the distance of x is 80, right? 80 meters east. So I'll put an 80 here. Dx dt, well, that's negative 22 plus 2 times y. Well, y, the distance of y is 60 meters. So I'll put a 60 here. Dy dt is up here. That was given to us. The rate of change, negative 25, equals 2 times s. Now, s is the hypotenuse. Well, if y is 60 at that moment and x is 80 at that moment, then by the Pythagorean theorem, s must be, let's see, here we've got 3 times 20, 4 times 20, so 5 times 20, that's 100. So s must be 100. So we'll put 100 in for s, and then we'll put ds dt on here. Now, last step, 7 is solve for ds dt. We got a whole bunch of numbers, so we can do a whole bunch of math. I'm going to grab a calculator. Let's see here. Where's my calculator? Here's one. All right, so I'm going to do 2 times 80 times negative 22. That's negative 3,520. Plus 2 times 60 times negative 25. I'm going to change that to a minus, I guess, is negative 3,000. So I'll make this minus 3,000 is equal to 2 times 100. That's 200 ds dt. So negative 3,520 minus 3,000, well, that's negative 6,520 equals 200 ds dt. And now all I have to do is divide both sides by 200. Divide by 200 on both sides. Divide by 200. That'll cancel the 200 over here. So negative 6520 divided by 200, and that gives me negative 32.6. So ds dt, the rate of change between the cars, is negative 32.6. And you could also write that as a fraction. You could simplify this fraction and write it as a fraction. But negative 32.6 meters per second. And because it's a negative value, we know that the distance is closing. And so there's our final answer. The rate at which the distance between the cars is closing at that very moment is negative. The way we would answer it is we would say the negative means closing. So what we would say is that the distance is closing, is getting shorter at 32.6 meters per second. We wouldn't say that it's closing at negative 32.6 meters per second. We would say that it's closing. That means the negative is interpreted as the word getting closer or getting smaller or closing at 32.6 meters per second. And that's the car crash problem.